Okay, hey everybody. So we're just going to continue on here with 12.3 basic rules of probability. This is going to remind you of your basic STA 2023 class. Nothing too fancy yet. That will follow in the sections after this. But basically, this right here is just notation to refresh on what we call the probability of something happening. An experiment is the actual action of me drawing a card, rolling a die, etc. The sample space would be all of the outcomes that could happen. So for a dice, as you see in my example here, I said our sample space would be all 6 numbers because you have a chance of getting all of those different ones. And then an event is a set of outcomes in that sample space. So events don't have to just be one task. An event could be, okay, what if I draw a 2 and it's a heart? So those are 2 separate conditions basically, but it's all one singular event. And then mutually exclusive basically is saying that they don't have any points in common for these events. So a collection of events in a sample space, E of 1 does not have the same points as E of j. And some notation to remember when we're going through all these definitions and the rules. E is usually what they denote for an event, and normally it will be E sub 1, 2, any number or maybe a letter. And then anything with a bar over it, even if it's not E, could just be the whole probability, would be the complement of the event. So it's just anything not in that event. So let's say it's the event that I roll a 1. Well, the complement would be all the other numbers. And then P of E or P of anything that goes in that parentheses, whatever event, is just the probability that it's going to occur. So this right here, rules of probability, these are very important. These are the overarching, foundational rules of probability. And the biggest one is the first one. Probability cannot be negative. It can be 0. So there could be a 0% chance that something will happen. But there also can be, it just can't be negative. I can't have negative 3% that I'm going to draw a 5. That doesn't happen. So if you get a negative probability when you're working through any problems, that's a good indicator that maybe you multiplied or subtracted or added wrong. So if E equals S, then the probability is 1. Well, think about it if I was saying okay, my event is I'm rolling a dice, my sample space is all 6 numbers. If I roll every single number, that's 100%. Right there. Or basically just think about it as if the event is the entire sample space, then it's 100% happening. So then if I have a mutually exclusive collection of events, meaning these all are don't affect each other or don't have anything in common, I can add them all together or union them together, and the sum of them would be that entire probability of all the events. And then the fourth rule, this is important. This is the complement rule. So I'll write that. That's how you spell it. If you forgot, it's not complement, to be nice. It's complement with an E. So basically, if I was saying, oh, I don't want, what's the probability that I draw a 2 out of this entire deck of cards? Well, or that I don't draw 2, something like that. That's one singular thing. Instead of going through and calculating every single probability and adding them all up and then trying to figure it out, you can literally just take that event out by subtracting it from the 1, because 1 is 100%. So conditional probability, this is going to be really important to us in all of these chapters, because conditional probability is saying that if event E2 occurs, given that E1 will occur, there's a certain probability of that happening. So given is the word used to describe that little bar. So let's say if it rains today, what is the chance that I brought my umbrella? That's conditional. So first, it has to rain that day. So if it doesn't rain, then that condition, that condition is totally out the window. So it's going to have a 0 there. So this is all conditional on one event happening in the other. They both affect each other. So if they both have positive probability, they're independent if, like, when I do out this conditional probability formula, that I would just get the same probability if I did both of them on their own. And that's just because, like they're saying, if event 1 occurs, it doesn't change the probability that the other one has occurred, we know it's independent, because if things are unrelated and don't affect each other, then we could just evaluate them separately. These formulas, this is basically just a rewritten way of everything above. You can rearrange these formulas to help depending on like what the question asked. That'll become more apparent in the example below. So we'll go over example 3. It has 4 parts. So I think I'm going to go back and forth. So suppose we draw a single card from a deck of 52 cards. That's like the premise. And then our first question is, what is the probability that a heart or a spade is drawn? Okay, so I'm going to go down to the solution. First, we define the events. E1, heart is drawn, and E2, spade is drawn. So usually you want to define what event is what to start. And they are mutually exclusive events because if you think about it, me drawing a heart or me drawing a spade, they don't affect each other because it says or. So it's hard because sometimes people think or and are the same, but and would imply that I like drew a heart and then I drew a spade. But or is saying, did I draw either or, which would be denoted by like a union symbol. So since they're mutually exclusive, we can say like they have equal chance of happening. But also if you think about it, I have 13 hearts out of 52 cards in general. That's 1/4, right? If I have 13, I guess this is how you draw a spade. Out of 52 cards, I have 1/4. So they have an equal probability of that happening. So that's what this is saying. And like I said before, we're looking for the union of these two because we want to know if either of these things could happen. So from probability rule 3, we literally just have to add them up to get 1/2. So you have a 50% chance of drawing one of those cards, which also tracks because about 50% of the deck is either a spade or a heart. So the second question asks, what is the probability that a card drawn is not a 2? So this is what I was discussing above with the complement rule. So first we define the event, which is just E. We're not even denoting it with a number, which is a 2 is drawn. So right here. So then P of E, like I did above, so we have what? 4 2s in the deck of 52. That gives us 1/13. But that's the probability that we do draw a 2. We want to know the complement of that. So all we have to do is subtract 1/13 from 1 to see that we get 12/13 as our probability of you drawing a not a 2. So then number 3 is a little bit longer because it says given that a red card, okay, right there, given, that's from that conditional probability above. Whenever you see given that something happens, it's probably going to be that 2 things are happening at once. So that a red card has been drawn, what is the probability that it is a diamond? So this is conditional because it's based off of first we have to draw a red card and is it a diamond? It's not both. It's not is it a diamond or a red card? It's both. So they already defined the events for us up here, E1 and E2. So if I go down here, starting here, we're taking that conditional probability formula. We know that the probability of either of these things happening would be 1/4 because it was mutually exclusive from above. If you add them together, you would get 26/52. So thus, if we put them over each other, 1/4 over 1/2, we would get 1/2. So basically, all you have to do is plug it into their formula for something this straightforward. And since the probability of it being a diamond is 1/4, we can see here that it is conditional and they're not independent because they're not equal. 1/4 does not equal 1/2. So we know that drawing the red card increases the probability that the diamond is also drawn. And so number 4, our last one, we just have to show that these two events, spade is drawn or 2 is drawn, are independent of one another. So P of E1. So the probability a spade is drawn, we also went above that. We went over that above, that's 1/4. The probability that we draw 2, again, we did go over that above, it is 1/13. So the intersection of these two things happening only happens once. We can only draw a spade that is a 2 once. Only one of those exists in the deck, so that's why it's 1/52. So if we multiply this together, we would see that they're equal because they are independent of one another. So P of E1 times P of E2, I would get 1/4 times 1/13, which is 1/52, which is also equal to 1/52. So they are independent of one another. We're going to go through this example. I did film this video separately because I didn't think you guys wanted to sit here and watch me write out the entire sample space. So if you see, like right here, I have written out the sample space of the problem. So the first line, suppose 2 dices or die are tossed. For each die, it is equally likely that you would get 1 through 6 dots. And so right there when I read that, I knew I had to create a sample space. And so if you see, I have, 1 through 6 on the top, 1 through 6 on the bottom, and then just went through, and these are all the combinations that you could get when rolling 2 6-sided die. And if you notice, that it would be 36 different outcomes. So our sample space is 36. And so we will start with the first part of the problems, part A. What is the probability that the total of the 2 dice will add up to 7 or 11? Okay, well, first, I'm just going to write A so we know what we're doing. So first we need to define our 2 events. So add up to 7. I'm kind of shortening it, but that you roll dice that add up to 7 or add up to 11. And so to get 7, there are about 6 different outcomes. So you're thinking 1 and 6. You can either have 6 and 1, 1 and 6 if I look over here. You could have 5 and 2 and 2 and 5. And you could also have 3 and 4 and 4 and 3. So there are 6 possible outcomes for that. And then for 11, if you think about it, we only can really get 6 and 5 and 5 and 6. So there are 2 different outcomes. So we want to calculate the probability of 7 or 11. So that would be the mutually exclusive rule, which is the probability of E1 or E2, so probability of having a 7 or 11. And that's just the probability of E1 happening plus the probability of E2 happening. So the probability of E1, like I said, there are 6 different ways to draw from the 36 outcomes. And for 11, we can only have 2 different ways to do that out of 36, which is 8 out of 36. And simplifying, 8 over 36 is the same thing as saying 2 over 9. So that's the answer to number A. So for B, we would like to know, what is the probability that the total of the 2 dice will add up to a number other than 2 or 12? So the key here is that they say other than, which kind of hints that we're probably going to use the complement rule. So we basically are going to do it the exact same way we just did A, but we will use the complement rule at the end. So let's define our two events of happening. So E1 would add up to 2, and E2 is adding up to 12. And so we're just going to use the same exact rule that we did before to find the probability of this happening. So P of E1, okay, so we can only get 2 one way. You can only get 1 and 1. If I go over here and look at my sample space, that's the only one over here that I'm highlighting. And so there's only one way to do that out of the 36 ways. Excuse me. And to get 12, there are only 2 ways I can do that as well, if you think about it. I can have 6 and 6, but I could get 6 and then another 6. So there is only one way to do that as well. So that gives me 2 over 36 as my answer. But if we remember, that's also the same thing as 1 over 18. So now I know the probability of me getting a 2 or a 12, but they want to know other than. So other than is when we use the complement rule, which is saying the probability of this happening, we just subtract it from 1. So 1 minus P of E sub 1 union E sub 2 is going to be 1 minus 1 over 18, which will give me 17 over 18. And that is the probability that you would get, that you wouldn't get either a 2 or a 12, some of those. So you can put those formulas together all at once. I just did it in 2 parts, but basically we're just using the rule we used before and the complement rule. So the last part of this question is, are the events E sub 1 first die shows a 3 and E sub 2 total of the 2 dice is 6 independent events. So if you guys recall from above, independent events would mean if one of them happened, it does not affect the outcome of the other. And since the sum of the 2 dice is 6, is dependent on the first die being 3, that would affect what's happening here. So I'm going to say not independent because we don't really need to prove it if you think about it. So the probability of me showing a 3 on the first try, well, that only happens, it looks like, 2 different ways. So 2 out of 36. So P of E1 equals 2 out of 36, or 1 over 18. And then E of 2 is the total of the 2 dice is 6. Are they independent events? Well, if you think about it, there are how many ways to get 6? Let's see. You could have 3 and 3, 4 and 2. So there's about 4 different ways. But it's directly dependent on P of E sub 1. So we would have to use the conditional probability rule, which means they are not independent. So that's like the intuitive way to go about this. You don't have to go out and prove all the separate probabilities for every single problem. So that's just a good problem to go over. You'll see more complicated ones in the following sections, so just stay tuned for more probability. Thank you.